Hello everyone and welcome to another video. In this one we'll be taking a look at the most recent C standard, C23, and most specifically this new operator, typeof, that is being partially or fully supported by most major compilers. As you already realized, I won't be editing this video. I'll basically do minor cuts here and there, but the intention is to have an edited coding session. This will be part of a much broader video series that is going to intend, or at least that's what I hope to be able to achieve, to develop a 2D platformer exploration game. I won't describe it any further because I don't want to create any false hopes, and I personally feel that I probably won't be able to achieve that much since I'm a solo developer in it. So without further ado, let's jump into our editor and create a file first. Since our game is going to be called Dear Universe, we can create our first source file, du.c, and the goal for this first video is to create a generic linked list using these C23 features. So before that, we can create our main function. I think that's the first thing we can do. Since I'm used to cut my videos a lot, I don't really know what to say while I'm typing, so I may speed up code for these boring parts. Alright, so we have just typed out our hello world using the standard C library, and I will be using this Windows development kit that comes with MinGW 64-bit basically. So the current version for my GCC is GCC 13.2, so it fully, in theory, supports or partially supports the features that we want to use, and we can basically compile our code like so. So this is going to generate an executable and we can run it, and this is going to print as expected hello world. Alright, so let's now start with the fun part. Let's begin actually by creating a non-generic linked list. So we can create something like a type definition of a struct. Let's call it I don't know, like list, or actually yeah, we can call it list float or something like that. And we can create a typedef above it. We are going to typedef the struct. We don't need this typedef actually, since we are going to use a trick I learned very recently taking a look at libuv library. And in that library they basically define their structs with this suffix, and then they typedef them with a different suffix, so they denote a struct and the type basically. And why do I need this? Because, as you may know, a linked list is basically a list of linked nodes. So we are going to need a link, and we are going to use this typedef type, and we need some data, so we can basically store a float inside this node. Alright, so one of the operations we may want is to add, remove, and traverse the list. And since we may want to also append at the end, well, yeah, we probably want to append stuff at the end. We probably want to let me think about it, because I'm actually going to use this data structure for a very specific purpose. So I don't really need to support everything, all of the operations that you may find in a list usually. So I think that the operations I'm going to need for my specific case are going to be append and for each, right? So since I want append and for each, I'm actually going to create a second structure and this is going to be a list node of floats, and this is actually going to hold our data, and I need to move this here, and this is now going to be a list node, and this is actually going to be the link. So why is this relevant? Because now my list data structure can have a pointer to the beginning and the end, right? I don't know if this is the best approach. I don't know if this is the simplest approach, but we can roll with it for now, right? Don't forget that I'm typing all of this out of my head. I didn't prepare any code, and this is basically live coding, okay? So now we can create the operation that I told you about previously. So we can say something like void list append, and this is going to receive a list. Yeah, we can receive it by pointer, right? And this needs to receive an element, so we can get the element. And now if we want to append an element to the list, we need to check a few things. First thing off is that we need to check if the end of the list is equal to null, and if that's the case, then I need to allocate a new node, and this new node is going to be this is actually the node, not the stuff, so I had a mistake there. So we need to create a new node, and we can simply say malloc, I think, yeah, and we can allocate a new node using size of node, like so, and we can have assert just to assert that this node is defined, okay, because malloc can fail, so we can basically assert that malloc did not fail. Alright, so at this point we created a new node, and we need to assign both begin and end to that node, so we can do that. Let's begin by begin, and same thing for end. Alright, so now we basically initialized our list if it hadn't been initialized already. So now we can basically this is actually needs to be like so, because actually if we create a new node here, so if we initialize our list with a new node, we can already this is I don't know if I'm overthinking, but I think we can compact this further, but this is quite interesting. Anyways, let me create an utility function here where I'm going to say list node float new. Well, do I want that? That probably not going to be useful. Yeah, we probably should just initialize it here, to be completely honest. So that is going to be our elements, and this is going to be null for the link, like so. Alright, so we basically reached this point. We created a new node, we assigned a null link to it, we assigned the element we want to append, and we set it to begin and end. And this is in the case where the list does not have any nodes yet, right? It doesn't have any nodes yet. Now we need to handle the case where the list does have nodes, and in that case, the only thing we need to do is to do list end dot link. So this is the next node appended to end, and we can assert that this is equal to null, right? Because otherwise the invariant that we assume in this structure no longer exists. So we can basically assert this. And what we want to do is create a new node, append it to the, or create a new node and set it to be the next node associated with our end. So we can say something like that. Actually, let me do this instead, right? So we can easily do this. And now what we want to do is basically say that list and link is equal to this new node, and that the list end is equal to node. So we moved the end of our list to the node we just created, right? So that's something easy. All right. So I think that's basically the implementation of our list append function, right? We will need to do some modifications, and I was a bit confused previously, because we will need to do some modifications here, but that's only when that will only be needed when we convert it into a macro. But for now this should work. So we can probably just test this code, for example. So let's create a list called L, and this is 0 initialized, and we can say list append L, and we can append 3.2, and maybe we can append I don't know, 4.7. So we can append 2 floats to it. And now how can I print this? So I can, for now, just to test things out, I can print 2 floats, right? One that is the begin data, and one that is the list end data, right? And since we only have 2 nodes in our list, one is going to be the beginning and the other one is going to be the end, right? So if I compile and run this code, I mistyped assert here, so let me redo this. Alright, so we did in fact print out the both floats that we just appended, and let's assume, for example, that we append an extra float in here, let's say 1.9, for example. So this end is now going to be 1.9 and the beginning is going to be 3.2, so we're going to print 3.2, 4.7 and 1.9 if I'm not mistaken, right? So yeah, actually we are going to print 3.2 and 1.9 because we are just printing two floats, the first and the last one, right? So that's basically working. All right, so now I need to create a macro where I'm just going to call it, let's say, list for each, yeah, we can call it like that. And in this list for each, we are going to accept our list, right? And this macro, or these macros that I'm going to create during this video series, I think I'm just going to follow the convention that Jonathan Blown uses in the Jai programming language and in his C++ code, if I'm not mistaken. That is, the it variable is reserved for the iterator. So it is always going to contain, in my case, right? In my case, it is always going to contain a pointer to the data stored in the specific node, right? So how would we traverse this list, right? So in a normal case, one thing that we could do, let me come here and actually put this code here before starting to program the macro, so I can explain to you what I'm doing. In a normal case, we could do something like this. So we would grab a node and we would say the current node is equal to the list begin, right? And then we could say while the node is not equal to null, so this will basically traverse all of the list until we find a null node, and the only null node we currently allow is the node that follows the end, right? And then we could basically say that node is equal to node.link, right? So we could have something like this. So we initialize a node, we have the termination condition, and we have the next node, right? And inside here, we could have something like this. We could print a single float, and we could have node.data, right? And we could just pass the data to the print function. And now this would actually print all of the floats inside the list, if I'm not mistaken. That's correct. So this would print all three floats, right? So now we can just convert this into a macro, and to do that, we actually need some stuff, right? Because we don't know the type of this list. Let's assume we don't know the type, no, because yes, I made this type hard-coded here, but this is just for this is just used for as an example, right? So let's assume we don't know the type of this list, right? So what would we need to do to create this loop variable, this node variable that we have here, right? And I think that this is a good use case for this feature, this type of feature, right? From C23. This is an operator that, given a const expression or an expression, it returns, like in air quotes, it gives you back the type. So you can, in theory, define a variable using typeof list, and here we can say the type of, let's say, the begin, for example, right? And this is equivalent to this. So this is equivalent to a pointer to list node float t, in theory, from what I understood from this feature, right? So we can say something like this. So create me a node with the same type as the begin node from this list, right? So I can say something like that, and then I can say list begin, right? List begin, and I can say then I can basically do the same stuff. While the node is not equal to null, node is equal to node link, right? So I can say something like this, and this would, in theory, already be a replacement for all of this code, right? Let me call this list, or I can keep calling it L, is not important. So this should be a replacement. This is complaining because list float t. Alright, so typeof doesn't give me a pointer. It is giving me, oh no, this is should work into, oh, I know what I did wrong, right? Because we need to, this is a macro, so we need to wrap our parameters inside parentheses, right? And this is already working. So you can see that the replace this macro expands to type of list begin, and this creates a node. Then we assign the list begin to this variable node. Then while the node is not equal to null, we say we keep traversing to the next node, basically. So this macro is already similar to the one we had previously, right? So we can say something like this, and this is already working, basically. But one thing that I particularly do not like about this is that we have this implicit node. So I don't know if I should have my it variable, so this implicit it variable containing the node itself, right? So containing this data structure, or containing my only data, right? So containing only the data. I think that it's probably more usable to have a pointer to data, if I'm not mistaken, right? Because let's assume we want to have similar behavior across multiple data structures. Then the most convenient thing to have would be the data itself being stored, right? So I don't really care about the container of the data, I only care the data itself. So now I have a doubt. I don't really know if I can have multiple, let's have hi here. Am I allowed to say something? Well, I'm probably allowed to do something like this. So let's assume I equals 0, I is less than 10, I plus plus. So I don't really know if I can have multiple variable declarations here, but I'm assuming that using parentheses and using it as an expression, or really actually no, because this doesn't allow me to do that. Can I do something like this? Is this allowed? So can I have something like that? Oh, I can. Alright, so this would be, this is undefined. Alright, so I probably can't really use, or can I? I'm thinking about a few stuff, if I can use a for loop or not. So let's say, well, let's come back to here. How am I going to be able to define an extra variable in here? Can I say something like float a? I cannot, right? Because this is outside and this is already breaks it. This is quite a interesting thing, right? So I really have no idea. Well, I could probably say something like that. Since, is this allowed? Yes, this is allowed. So could I say float this is also not allowed. This is quite interesting. I need to think about it. How can I possibly have an implicit it variable that contains the data itself if I'm traversing using another variable? Maybe I do want to introduce a new scope. So one solution that I thinking about to this problem is to have an extra parameter in our for each macro called code, and I can simply embed code here. Right, I can simply embed code here. So instead of using this macro like this, you would use this macro like this, right? Like so. I think improperly terminated. Okay, we just, yeah, something like that. Is this something I want to use? Is it convenient for the user to call this macro like this? That's what I'm thinking about. Because if I do this, then it becomes trivial to create new scopes like so, right? So then I can just do something like this. I can simply create something like this. I pass in here the code, right? And this requires some extra slashes, like so. Right. And I cannot use that, I think. Or can I? False is undefined. It's because we need to import stdbool. Alright, so that's one option, right? Even though I don't particularly like this syntax, I would much rather have something like this, where we would simply call it like this. But to be honest, the difference isn't that much, right? And this specific syntax for the macro allows us to actually have a very interesting abilities, right? Because now we can just simply create new variables. Let's say we have a new variable with a type of begin data, and this is going to be our iterator, and this is actually going to be a pointer to begin data, right? Like so. And now I can open another scope, right? So we can have multiple scopes now. We can have multiple scopes, and inside this scope I can assign the iterator to be equal to node data, to pointer to node data, right? So about this. All right, so this is actually this proper syntax to use typeof. So now we would say something like it, and this would be our iterator, right? I think I am happy with it. I think I'm happy because now we can say something like that, and this is going to work. And furthermore, we can probably have something better for this. We can probably so this is going to create collisions. So we have, if we have a list inside a list and we traverse with both stuff like that, so if we have something like this and inside there we have this like so if we have something like that, but that is also not going to work, to be honest, my theory. So this and this is missing that. Oh, that's not what I want. I'm taking screenshots without, yeah. Alright, so this, the problem with this is that now we have two variables, both named node, right? Both named node. So I think we have line, right? And we have column. I hope we don't have column, right? We don't have column. So we have this line macro. We have this line macro. We have that line macro. So to prevent collisions, since this is all going to be placed inside a single line, right? Because we are copy and pasting it, and these slashes basically they tell the preprocessor, oh, don't ignore the new line, right? So use a single line. I think we will need to go deeper, right? I think we will need to go deeper and have another macro. Let's say list for each 0 or something like that, or I don't know. Yeah, this is going to work, where we give the list, the code, and well, is this going to work? Is this going to work? I don't think this is going to work. Well, what's the behavior? What's the behavior of this current implementation? This is not my command line, this is my command line. Alright, so this actually works. This is going to print each individual one of them. Right, because we are opening a new scope. So if we add something like this, int a, and then we define another int a, these shadows correctly. I didn't expect it to work like that. So let's say I have int a with 3 and I have another int a with 4, and this second int is inside another scope. I can print alright, so I'm back. So we were testing if C shadows variables properly, right? So we can have a test, right? So let's say we have for loop. We begin this for loop with 1, and then I say a is less than is this really what we want? Well, let's actually have a proper test, right, for this specific case where we have for each inside of for each, right? So we can say that this is our list 1, and on the so on the outer loop we are going to have list 1, and we are going to have another list, let's say list 2, and this list 2 is going to have all the numbers with, basically larger. And what is this complaining about? Oh, list 1 is undefined. Okay, so we can have list 2 on the inner loop, and here we are going to print the current iterator, and here we're going to print again the current iterator. So this iterator should be basically relevant for this, and this iterator should be for this. So here I can say list2, and here I can say list1. So if I print this, I'm going to print actually all the correct alright, so this actually works. So this actually has proper shadowing. So I have list1 prints the first value 3.2, then I print all three values from list2, right, 31, 41, 11, then the second value from list1, 4, then again three values from list2, then one value from list1, and then again three values from list2. So this iterator is actually going to work correctly. Okay, so it's going to shadow correctly, variable shadowing. Alright, so I'm happy with it, right? So this actually is good, correct code. Alright. Yeah, probably because we use this do while stuff in here. I don't know. I'm not really sure to how C is shadowing variables currently, since I've been programming in C89 and C99 for more than 8 years, so I have no freaking idea of how C is doing that in modern times, let's say, but it is working in fact, right? And actually, to verify that, we should say something like this, right? We should specify that we want C23 standard. What is C2X? Is it similar? Is it the same thing? So right. Alright, so the standard is not C23, is C2X, right? Alright, so it's working. So if we compile our program according to the C23 standard or C2X standard, this code works, it shadows the iterator properly, everything is working basically. Okay, so let me actually try now, okay, to convert these codes into generic declarators, right? So we can have something like this. We can have another macro. We can call it list decl, right, or declare list. We can have the type, probably, right? We can have probably a type, and now I only need to move these codes into the correct places. So here I'm going to need to compile like so. You can say type, and here I can say type. So these two hashes, what they do, they concatenate the token that precedes them with the token that succeeds them, right? So that's nothing special about it. Let's experiment with this and say float. What is going to generate it by this? Okay, so it as you can see, it expands to the correct stuff. So typeof struct list node float s, list node float t. So this is the behavior of these two hashes, right? So alright, so we can move now these two here. Okay, and we need to add the correct stuff in there. And now we need here, instead of specifying list node float s, we need to once again do this trick. So we specify it like that, and here we need to specify it like that. And now for type, well, I don't actually want to use type here. I want to use T. I think T is probably a better name, right? So I can replace all of this by T. I think it's a lot more explicit what is going on. Oh, I need to reformat this stuff. Bear with me, right? Bear with me. And now for data, I can simply use T. Alright, so this macro is currently defining the list node for a specific type, right? So, and we are using it, right? And we are already using it. So let's test it, right? So let's test it. It is working. Okay. So now, let's keep working, right? Let's keep moving. So now we need to define this for the list itself, the list structure. We can use the same trick. So now we defined it, the type definition for a generic type definition for the specific type of this list, and we can move the struct as well to here. Actually, before doing that, I want to, this should be here, I want to replace this, and this is going to be the same as that, right? So this should already be generic. Oops. This should already be generic. And one thing I may want to add is some white space in here to make it more readable, right? These are macros, but they don't have to be unreadable, to be honest, right? So they have clear separation on what are we defining. So first we define a generic type definition between the struct and the type. Then we define this, the generic node. Then we define same for list and the generic list. Okay, now we are calling this macro here, and we are basically declaring it. So we are declaring a list of floats, and this should keep working, right? So if we recompile and run our program, this still works. That's wonderful. Now we probably want to change this function to behave like a macro, right? So we want to move this over here, and we want to create a macro. And I think it's properly written. Should I create something like this? Is this prettier? I don't know. Right, it doesn't matter. Right, am I writing it properly? Yes, I am. Alright. So we have this list append macro, and we need to create it, basically. Right, so we need to accept a list and an element. Right, an element. So now we can remove this declaration and replace it by a do while, probably. I think so. So what this is going to do, this is going to isolate our code in a specific scope. I basically don't need to change much. I actually don't need to change much. I just need to add our slashes, and this should probably keep working, right? So let's keep adding this stuff. keep adding this stuff. And the only change we need to have in here, it is this thing, I believe, right? This list node float t. So here we need to use the same trick we used here. So we can probably just yoink that and create like so. And since list begin is already a pointer, we don't need to put the pointer in here, right? And so yeah, I think this is basically the bare bones of what we want. This doesn't need to be here, this can be moved out, right? So we can basically have this, right? We can have we can declare a list of floats, we can declare a list of integers, right? So declare two lists. I can have list int L2, and here I'm going to pass some integers like 100, 101, 102. L2 is going to be an integer, so I can modify this to be a %d. And now the real test is that we have two lists of different types, and the implicit iterator has the same name. So is this going to work? Oh, alright, so we actually need to use the new macro we created. So instead of using this function, we need to use this generic macro. And this has some problems because I forgot, obviously, to wrap list around parentheses. And talking about that, I also need to wrap around elements around parentheses. To be honest, that's probably the best approach. Can do that. And here do the same stuff. Like so. And here I can do the same thing. Alright, so basically I think that's the fix. So if we see here, yeah, it's no longer complaining, and if we compile and run, did this work? Yes, it did actually. I think it did, right? Let's say I have a list of sharp point. Is this a thing? Alright, so our current implementation does not accept pointers. So if I do something like that, is this going to work? Is this going to work, or is it going to be okay? No, it's complaining. Alright, so that's unfair. That's something bad. That's definitely bad. So one thing I think we can do is to have a type def sharp pointer to string, and this should fix our problem, right? This should fix our problem, so I can have list string t. But another fix for this, or this is basically just the API of these macros, right? Instead of just passing t, I could pass type name and then the type itself, right? And I would no longer have this problem because I would need to declare the type name and t. But for now, I think I can simply do stuff like that, right? So I have a list string t, and let's say I have a few strings, hello world from a list, right? And here I want to print my strings. Let me test it. Alright, so I think this implementation of a list works perfectly fine. So we have the append operator. So we have the append operation that appends an element to the end of a list. And we have the list for each operation that basically traverses a list with an implicit iterator that is basically called it, and it is a pointer to the data field inside our node struct. So anytime you are traversing a list, you don't really need to think about nodes and pointers and stuff like that. You just have access to the data itself, and that's it, right? Yeah, there's no complications with it. And this basically supports, this implementation supports nested loops for lists with different types. So here the outer loop is a list of type float, and here the outer loop is a list of type string, and the string is just a sharp pointer, right? So a C string. I can actually call it sister, right? A C string. It is probably better stuff. So this is a C string, and as you can see from our compilation and running, so if you compile and run, as you can see, the iterator has different types depending on where, in which scope it is being used, right? In which scope it is being used. And I think that's all, to be honest. For this specific implementation, or the research, because this is definitely not going to be the final implementation. I just wanted to research this new feature from C that allows us to have actually pretty good generic macros, right? Very type safe generic macros. And not only that, it allows us to have type safe generic macros with proper variable shadowing, which is something new for me, in C at least. Yeah, and probably in the next video I'll be working on allocator, and we will need to introduce the concept of allocators to our data structures. And note that this list is not going to be used by itself, so I'm never going to use a list to store ints, right? This is stupid, right? I'm going to use a list in conjunction with other data structures. So I think that's basically it. At the end of the day, we implemented 3 macros, all of them generic, type safe, and yeah, I think this was a success in terms of researching this C operator, at least for my current version of GCC. That is 13.2. I am using MinGW, by the way, MinGW 64-bit with 13.2 GCC version. This is working, right? So that's it. Thank you for watching, and I see you in the next video.